So we're going to go ahead and start section 5.4 notes. Um, Again, I have this slated for 2 days. I'm not sure if I'm going to need both days or if I'm just going to need a piece of a day. I'm not really sure because I have removed some material from it and I just double checked the homework. There is nothing in the homework from the material that I removed, and there is nothing in, or on, I should say, the test from the material that I removed. So you don't have to have any worries about that. I got you covered when it comes to that. And trust me when I say the stuff that I'm cutting out is not useless. It's just, unless you're going to specialize in some kind of intense trigonometric field, you will probably never use the identities that I'm just going to go meh to. All right. So don't worry, I'm not stealing anything from you. They won't be necessary for calculus or anything. You will be just fine skipping the things that I'm skipping. I promise. But we will begin with some extremely important trigonometric identities. In fact, I'm surprised that the textbook authors put these after the section 5.3. I mean, maybe they did it that way we had the ability to prove these things are true, but these are much more useful in my opinion. We're going to start with the double angle identities. Literally what happens when you double a special angle, so we can do it by hand, or what happens if you double any old regular angle. Of course, that would be a calculator question, right? But we've been working with, let's see, we've been working with 30s, 60s, 45s. Of course, if you double all those, you get another special angle, you know. But do you really want to have to go through the process of tracking down a triangle somewhere else on the quadrantals when there are double angle identities that can get you there faster? Also, double angle identities are very useful for trig proofs. Everybody's favorite thing, right? All right, so what we have? Sine of 2u equals 2 sine u cosine u. Very useful, pops up all the time. The cosine double angle formula is neat because there are 3 different variants of it. The most important one is cosine squared minus sine squared of u. Now the other 2 come from this first one, because remember, you can isolate cosine squared in the Pythagorean identity sine squared plus cosine squared. I'll use the u because that's what they're using. You can get this cosine squared by itself by subtracting sine squared u from both sides. You could then substitute into this one for cosine, and that's how you would get that one. Or you could isolate sine squared u by subtracting cosine squared from both sides, substitute right there, and that's how you would get this one. It's that simple. So there are 3 of them for cosine, and this one we actually accidentally derived in yesterday's notes. The question that I had yesterday in the notes was, what is tangent of 2 alpha? And we had to break that down into tangent of alpha plus alpha. You guys remember me doing that and then simplifying and going, oh look, a double angle identity. There it is. Okay? So there you have it. These are on the reference sheet that you will have for your test. However, you want to have memorized sine double angle and cosine double angle. Those are going to come up so often. You really do want to have them memorized. You will be much faster. Am I forcing you to memorize them? No, like I said, they're on the reference sheet. But those are ones that I do have memorized because by accident, because they come up so often. And because I write my identities every time I'm going to use one, I've written these identities, oh, I don't know, about 100 gajillion times. Okay, so they do come up very, very often. We'll start with one of my favorite things to do, and that is a trig proof. We will prove this double angle identity. But how could we possibly do that? We could do it the same way that we accidentally derived this one yesterday. We can use the sine angle plus angle formula. We could say sine of 2u is sine of u plus u. The sine sum and difference formulas go sine cos, cos sine, same symbol, sine cos, cos sine, same symbol. And this is multiplication. Does multiplication care about order? Of course not. Sine times cosine of u is the same thing as cosine of u times sine times u. So you just literally write 2 sine u cos u, and you're done. It's that simple. Because multiplication doesn't care about order. These two things are identical. I'm adding two identical things. Oh, I have two of them. How about that? Pretty easy, right? Maybe that's why the authors put it in this order, so you have the ability to derive these. These are more useful in my opinion. Questions on that one? Or pretty simple? Stunned silence. Okay, great. All right. It makes quality YouTube content. The power reducing identities. Look at these bad boys. So not only could you say that sine squared u is 1 minus cosine squared u, or not only can you say cosine squared u is 1 minus sine squared u, you could say they're also equal to these fractions that use double angle identities. They're quite easy to prove, and they're quite easy to derive, to be honest with you, using this and these. Insanely easy to derive. I don't remember if those are on the reference sheet or not, but I can tell you where they're not. They're not on the homework, and they're not on the test. So I'm going to skip this question. If I have time for it, I would be happy to come back and show you how to do it, and that is only because I think it's valuable to see lots and lots and lots of trig proofs to help you start thinking your way through problem solving them. For now, I will skip it. We will check on time at the end. I'm going to be real with you. It's insanely easy to prove. Now this one would be using the power reducing identities that I just showed you, turning cosine to the fourth power into other trig functions that do not have exponents. It takes this much work, but it's not on the test and it's not in the homework, so I'm going to skip that one. So basically anything that had to do with the power reducing identities, I'm not doing. If I have extra time, I will go back and I will do them. But they're not assigned. They're not being tested. Again, the only reason why I would even bother showing you is because I think it's valuable information to see lots of problem solving strategies. I really, really do. So we got the double angle identities that are important, and I'm going to have you use them, and you're going to be finding the measure of double angles by hand. And then we have something really special for you, the half angle identities. Now the half angle identities can be derived by using the double angle identities and the power reducing identities that were on the first side of the paper. I will not be having you prove the double angle identities ever. I'm just going to have you using them. And they're on the reference sheet. So no, you don't have to have them memorized, but you do need to be pretty darn quick at using them. Notice this plus or minus. That doesn't mean you will get two answers each time. What that's telling you is your answer could either be positive or it could be negative. And we will have to figure out which one it is based on where we were in the quadrantals. Isn't it neat though, they both have cosine in them. Sine is 1 minus cosine over 2 square root, and cosine is 1 plus cosine of u over 2 square root. Now because tangent can be written as sine over cosine, it ends up having several different formats. And basically you just end up picking the one that would be easiest for you to use in those situations. So yeah, they're not incredibly difficult to derive. Using the power reducing identities and the double angle identities, they happen pretty easily, to be honest with you. But I won't have you do it. But we will use them. Starting right here. Popping right through these bad boys, aren't we? We've only done one thing. It says to use a half angle identity to find an exact value for sine of 3 pi over 8. So last couple of days when we were using the multi-angle identities, excuse me, the sum and difference identities, my apologies, we were we were able to evaluate trig that was over 15, or excuse me, that was over help my brains, 12s, pi over 12 radians, multiples of 15-degree angles. These are multiples of, or excuse me, halves of 45-degree angles. These are multiples of 22.5 degrees, because an over 4 would have been a 45-degree angle, right? So this is 22.5 degrees times 3. Is it 67.5 or something like that? Yeah, we can actually do this by hand, and we will be using the half angle identities to do this. What we know is that our angle, 3 pi over 8, we recognize the over 8 as being a half angle. That's the key right there. Did you recognize that an over 8 was a half angle? So even though I'm going to give you the identities, you have to know when to use them. You have to recognize double angles, half angles, sum and difference of angles. That's the hardest part. Are you fast at recognizing? I see an over 8, I instantly go, oh, that's half of an over 4. This is a half angle identity. That's what I've trained myself to look for. So I identify my half angle. I say my angle cut in half happens to be 3 pi over 8. That is my angle cut in half. So what was the original theta? How would I have found the original theta? Well, you would just multiply both sides by 2 to find what the original theta would have been, to get that theta would have equaled 3 pi over 4. Mr. Arm, why are you doing that? Allow me to flip my notes back over and show you. These identities involve, well, they have a u, but imagine that says theta on one side of the equation, but on the other side they have half of it. So my identity that I'm going to use is going to involve a cosine of 3 pi over 4. So I needed to know what was going to go here in this formula. That's why I did that. Before I jump into the formula though, remember what I told you? You're not going to get a positive and negative answer. You're going to get a positive or a negative answer. So what you do is you ask yourself, where am I? And would this be positive or negative for the kind of trig that I'm working with? 3 pi over 4. That's in quadrant 2, where sine is positive. So when we go to use the half angle identity for sine, we're going to use the positive version of it. You guys cool with that? I'm just going to write the identity on the page up here so I don't have to keep flipping back and forth, maybe so you don't have to keep flipping back and forth. Plus, the more times you write it, the more likely you are to accidentally memorize it. I think I can squeeze it in right up here. So we have sine of, I'm going to use theta instead of u since I've already got thetas on my paper. Theta over 2, we said we're using the positive square root fraction, and we have 1 minus cosine of whole theta, not half theta, over 2. Oh, all we're going to have to do is evaluate cosine of 3 pi over 4 to make this easy. I mean, it'll just be a simple answer from there. Okay, so let's actually get to it. Sine of 3 pi over 8, which is this part of the formula, is positive square root of 1 minus cosine of whole theta, not half theta, 3 pi over 4 over 2. We've already identified this being in quadrant 2, so I will draw my 3 pi over 4 triangle in quadrant 2. Of course, picture never drawn to scale. Over 4s are 45-degree reference angles. So squeeze a little 45 degrees in here like that. and then I'll put my known side lengths. 45, 45, 90 is a 1, 1 root 2. I'm in quadrant 2, where the y's are positive, the x's are negative. Square root of 1 minus, and now it's time to evaluate cosine at 3 pi over 4. Cosine is x over r. So it's negative 1 over root 2. Ew, look at this. Fractions in fractions with radical denominators inside a radical. Holy guacamole, right? Bad news, we do have to clean it up. We do have to clean it up. Rationalize all denominators, so on and so forth. This is true. 1 does equal root 2 over root 2. But my strong suggestion is rationalize before you combine. You're not wrong, and it would still work. But if you don't mind distributing radicals, do exactly what you just said, combine them first. I don't like to distribute radicals, so if I can avoid it, I try to. So I'm just going to call this thing root 2 over 2. If you'll allow me to do that. So the top will be 1 plus root 2 over 2. And then mechanically using the same logic that you just used, instead of saying 1 is root 2 over root 2 now, you would say 1 is 2 over 2. Yeah. Look at all these 2's. Isn't this fun? I don't know if you've noticed, but I've started writing smaller, smaller, smaller. I have to make sure that I got enough space here. Math is going to have to get short. What's that? Get skinny, man. Get skinny. Actually, now it's going to have to get short. So here I have a 2 plus root 2 over 2. Crap, I missed a over 2. Ah! Whoopsie. I'm sorry, guys. There's too many over 2's. This was supposed to be my numerator. You guys know that dividing by 2 is the same thing as multiplying by 1/2, right? Okay. So inside this radical, I have 2 plus root 2 over 2 times 1/2. So the final result is the square root of, well, that's not true. The final simplified fraction result is the square root of 2 plus root 2 over 4. And the very, very last step is I could take the square root of the denominator. So this half angle identity gives us a result of the square root of 2 plus the square root of 2. Look at that. It's called a nested radical. And all of that is over 2. It's almost a comical answer, like I just wanted to have a bunch of 2's in radicals, right? But that's actually what it equals. Sine of 67.5 degrees is that. Now, there were a lot of 2's, a lot of fractions, and a lot going on. Is there anything I need to clear up for anyone in the room at all? Please, let me help you. Help me help you, as they say. All makes perfect sense? Yeah. Ah, and right. So this is actually the real question, because if you're taking a test, it's not going to say use a half angle identity to. It's just going to say evaluate sine of 3 pi over 8, and it wouldn't say anything about half angle identity. So how did I know, if I hadn't read the title, how did I know to use a half angle identity? That's the true question. So denominators that we're used to. Okay, let's talk about that. We are used to over 3's. We're used to over 6's, and we're used to over 4's. I mean, we're used to over 2's also, but that doesn't really, You know, if you cut that in half, you just have a standard quadrantal. So let's not talk about that. Well, a half of this is going to give you over a 1.5. That's never going to happen. You know, if you see over a 1.5, that's just the same as saying times 2/3, right? If you cut this in half, you get an over 3 again. Why wouldn't you just use one of the things we already know how to do with over 3s? Wait a second. What am I smoking? I'm going backwards. I was doubling. Sorry about that. What I was trying to say, if you cutting in half doubles the denominator. There we go. Head removed from rectum. So yeah, when you cut an angle in half, you double the denominator. You double this one, you get a 6 again. That you would just use your standard trig for. But if you double this one on the bottom, this one will convert to an over 12. So over 12s are really good options for half angle identities because they're half of sixths. And if you cut this angle in half, double the denominator, you get over 8s. So these are your targets for half angle identities, your over 12s and your over 8s. Do you always have to use a half angle identity for over 12s? No, you don't. The last example in yesterday's notes was an over 12, but I converted it to degrees, and I used a sum or difference identity. So if you see over 12s, you actually have more than one option. Your over 12s, you could either use a half angle identity, or you can use a sum or difference angle identity. It's whichever one you're more comfortable with. But the over 8s scream half angle because that denominator is double a fourth. So those are the ones that you're hunting for if you want to use half angles. Because yeah, the test isn't going to say use a half angle identity, use a sum or difference identity. It's just going to say evaluate, or it's just going to say prove. And you go, okay, well, the only way I can prove this is with a half angle identity or a double angle identity or sum or difference identity. Good question. Good question. See, this one says use a double angle identity to solve. Would it have said use the double angle identity to solve on the test? No. It just would say solve for x. But the only way you could possibly do that is if you didn't have a double angle here. Because look, this one's argument is not a double angle. It's kind of like a trig proof where you have to go, well, where am I trying to get to? What do I have to do to make them similar to one another? I'm feeling purple. I'm going to do this one in purple. Yeah, sine of 2x, cosine x. I mean, the graph of this is a sine wave that completes a period once every pi. This is a period once every 2 pi. I mean, these things, they're going to intersect a bunch of times. And I just can't visualize that graph in my head. That's okay, though, because I have a double angle identity for this. Sine of 2x is 2 sine x cos x. And we set it equal to still cos x. Let me tell you something that you never, ever, ever do in algebra. You never divide by the variable you are solving for. So the last thing you would do here is divide by cosine x. You don't do that. Never divide by the variable you're solving for. Instead, you get all of those variables to one side of the equation. Subtract this cosine x from both sides. And we solve from here. What do we typically do when we bring all our variables to one side? Factor. We typically factor, and this is one of those times. There's a GCF. You can see it, right? It's cosine. Cosine x is our GCF. So we can factor out a cos x and get to sine x minus 1. Since it equals 0 and is in factored form, we just need the parts to equal 0. Our solutions will be found when cosine x equals 0 and when 2 sine x minus 1 equals 0. Yep, and that's what we would do there. So really we're hunting for when cosine x is 0 and when sine x is 1/2. There. Cosine is 0 when there's no x values. Because remember cosine, and not this x, the quadrantals x, I mean, the coordinates. Since cosine is x over r, where on the quadrantals would I have no x value? Where on the quadrantals would the x value be 0? Someone said pi over 2, someone said on the y-axis. It's not just pi over 2, it's both times you're on the y-axis, both quadrantals that are on the y-axis. So we're talking when we are here, because this is 0, 1, and when we are here, because this is 0, -1. So those two answers are pi over 2 and 3 pi over 2. Not bad, right? Easy peasy lemon squeezy. And sine is positive in 2 quadrants. Which 2? You guys are allowed to talk to me, 1 and 2. I don't know why people won't talk to me. My pictures are never drawn to scale because I don't want to. Sine is y over r. So I have a 1 here, a 1 here, r's are 2. And Pythagorean theorem tells us that that other side must be a root 3. And this one's a negative root 3 because of where it is. But what size is that reference angle that's creating that triangle in degrees? What's always across from a 1? A 30-degree angle. Yeah, well, in this kind of triangle, it's a 30-degree angle. And clearly this is a 30-degree angle as well as a reference angle. But what in radians, what are these over 30s? Or these over 30s? What are these 30s? What's that? Pi over 6. So this one's pi over 6. And this one would be a pi over 6 before pi. 5 pi over 6. And there's your 4 answers. We do have to be careful when we're solving trig equations, make sure that nothing ever would have made us undefined, but we're dealing with sines and cosines only, and they are never undefined. Since there's no fractions, we don't have to worry about dividing by 0. I mean, obviously these answers are written in numeric order. On the test they would be. So as long as you're comfortable putting them in order, you're good to go. It'd be pi over 6, and then pi over 2, then 5 pi over 6, then 3 pi over 2. That's the order. But please feel free to ask me any questions if you got them when we hear them. No? Well, the dead giveaway is that one of them has a double angle. I mean, this 2x just is supposed to jump out at you. You go, oh, it's double. Especially because this one's argument was not double. For example, I'm just going to write something. I'm not trying to solve it or anything. I'm just trying to set you up for something. If it had said, let's just say it says cosine 2x equals cosine squared x. I don't even know if this has solutions. I'm just saying. You would look at this and you would go, okay, that has a double angle. That doesn't. There are 3 double angle formulas for cosine, and one of them does not have sine in it. And that would be your target. Because then you could bring all your cosine squareds to one side and then just have numbers on the other. The identity I'm talking about is 2 cosine squared x minus 1. So you would subtract this cosine squared x, add 1. You'd have cosine squared x equals 1, so cosine x equals plus or minus 1. So yeah, it has 4 solutions. Okay, but you just kind of you see that and you go, all right, this has double angle, this doesn't. I need this to be able to play nice with this. I'll pick an appropriate identity. is basically what we do. This is probably a homework question, to be honest with you. It's probably in your homework. Now, if both sides have double angles, I mean, by all means, try to use that knowledge, you know. But if only one side has double angle, I would use identities to get rid of the double angles. You can't tell, but I'm looking at you as I'm saying this. And lastly, more trig equations. We're going to solve this, and even if it hadn't had a title, I would have noticed that one of the arguments has a half angle in it and the other does not. So the very first thing I would have done was try to get rid of the half angle. Well, how do you get rid of the half angle? You use an identity that does not involve the half angle. Namely, the identity for sine of x over 2. I'm just going to write that off to the side in purple, and I'll do this one in green. I'm feeling green. So sine of x over 2 is, and remember this could be positive or negative, square root of 1 minus cosine x over 2. We're going to use that identity here. So here's me substituting in for my sine squared, but it is squared, so I'll go ahead and put that exponent out there. I write plus or minus square root of all of that jazz I just wrote a second ago. And the cool thing about it is, what do squares do to radicals? You guys can say it, you know. No one's talking. It cancel them. A female voice was whispering it, but for some reason she wouldn't say it loudly. I'm assuming it was Casey. But yeah, you could square this radical and it would cancel it. But Mr. M, there's a plus or minus. I know, but you know what the great news is? When you square positive, you get a positive, and when you square negative, you get a positive. So it actually doesn't even matter. These symbols, plus, minus, and radical, are all canceled by that. So we're left with sine squared x equals 2 times 1 minus cos x over 2. And then, well, it simplifies even more because, you know, times 2 divided by 2 cancel. I have sine squared x equals 1 minus cosine x. These are very different statements, aren't they? I need a way to make them be able to play with one another using an identity. Yeah, sine squared can be turned into 1 minus cosine squared. That is the identity that we will use there. Now I only have cosines. I have variables squared and variables not squared. The only way to handle that is to bring everything to one side, correct? I don't like negatives in front of my squared objects, so I will subtract this one and add this cosine squared. Of course, these are not like terms, obviously, right? So on the left side, I get a 0, which is good because we're thinking factoring. And on the right side, the 1 and negative 1 cancel, and I'm left with cosine squared x minus cosine x. Which, yeah, they factors. GCF, cosine x. Never, never, never move this cosine back over here and divide by cosine. Don't do it. Never divide by the object you're solving for. When you do that, you eliminate solutions or discontinuities. By the way, this is an exponent, not a 2x. I should have made it a little bit smaller. Since it's factored and equal to 0, we just set the parts equal to 0, and we are ready to rock and roll. Our answers are going to happen when cosine x equals 0 and when cosine x equals 1. And I forgot to type that I only want the answers from 0 to 2 pi. So let's go ahead and write that. Wait, or did I type it on yours? So yours is missing the domain as well? Yeah, let's just go from 0 to 2 pi. Instead of finding quote unquote all, just go from 0 to 2 pi. Well, we just talked about when cosine x is 0. Cosine x is 0 in the quadrantals when you don't have an x value because this is x over r. So that's going to happen here when you're at 0, 1, and here when you're at 0, -1, because, like I said, x equals 0 there. But cosine equaling 1, since it's x over r, you need the x value to equal the radius. Since the radius is always positive, this happens when your x value is also positive. So it's going to happen in one place. When x and r are the same and x is positive, that happens here at 1, 0. That is 0 and it is 2 pi. However, it does not include 2 pi because I put a parenthesis on it. I mean, it's the same answer, basically. So our answers are x equals pi over 2, 3 pi over 2, that's these two, and 0. Crap, I should have written 0 first. Well, whatever, there you go. Those are your 3 solutions. Are there any questions on it before I stop the video? Because these good questions, we got to hear these things. Stunned silence. Man, I'm good.